Let's try to talk about the open cover characterization, which I think you're more familiar with. So in carotters, which is rather unusual in analysis books, you define that compact sets are compact. So compact sets must be complete and totally bounded. But probably in the previous class you have seen this more common characterization, which I'll try to explain today a little bit more about. It seems obscure, but yeah, perhaps you know what's the motivation for this definition, which was, I think, given by Hausdorff in the, I think, somewhere in the earlier part of the 20th century. You know Hausdorff, right? He's a good fellow. All right? Quite a few definitions will come your way. So his definition of compact sets was that, maybe it actually was before that, but definitely in general topology, his name appears quite a lot. So M is compact if every open cover has a finite subcover. So first of all, do you understand what it means? Every open cover has a finite subcover. So what you think about, what I think about at least, is that you have a box of tissues, and those tissues are your open sets. And those tissues can cover your space. In other words, so actually let's see if you see the difference between the totally bounded definition and the general open cover definition. How is this definition different from what we spoke about when we talk about totally bounded sets? What's the difference between the open cover definition and the definition for totally bounded sets?
In totally bounded, you're picking uniform open sets, which are all open balls.
Right, exactly. So when you think about totally bounded, the picture that you have is that here is your space M, and you cover it always by napkins that are all of the same shape and size, always of the same shape and size. So this is epsilon, this is epsilon, and you just have finitely many such covers, right? Finitely many. They're all the same. Correct? They're all exactly the same shape, and you can do that for any epsilon. So the manufacturer can give you napkins of arbitrarily small size. Radius epsilon is arbitrarily small, and you need only finitely many to cover. Now, it's more cruel when you are dealing with, so this is totally bounded here. Now, if you have compact space, then the napkins can be of very, very irregular shape. So something like this, maybe something like that. And something like this. Okay, so so the box of napkins can be just containing quite different shapes of open sets. Okay, so that's the difference. So in particular, compact, of course, is much more general. So you can cover the set M obviously by napkins of this shape, because you can cover it by napkins of all possible shape. Correct? Now, question 2, which is maybe slightly harder, is what's the motivation for the second definition? Why would we think to characterize compact sets? Sets in terms of open covers. All right. You want to say something?
Yeah, because I was thinking like sometimes you don't really have the definition of distance, so you don't really have the uniform size of the site, so you have to like.
That's a very good point, right? So in general topology, you don't have a definition of distance, perhaps, right? And therefore, it makes no sense to speak of balls of uniform shape. That's one example, but still. Why would we even care about compact sets? Where those ideas are coming from? So this is what I'll try to explain. It's actually very simple, except the problem is how do I describe it with words rather than with just a picture. So to answer, let's first of all consider. I should actually say that compact sets behave very much like finite sets. Okay, compact sets are like finite sets in terms of continuous functions, and that's what I'll try to explain. So here is why. So first of all, suppose that we have a set f is a function from the set 1 to, let's say, all the way to n into R. I have this function, and this function has a maximum and minimum, correct? This, I don't need to know anything about this function to know it has max and min. Because f of 1, f of 2, f of 3, just a bunch of points. And those points are going to be mapped to a bunch of other points that clearly there is a maximum and there is a minimum. Okay? So if a set is finite, we have maximum and minimum. So when you are trying to consider which sets have this property that every continuous function has a maximum and a minimum over that set, then you can try to understand this in terms of open covers. So here is, may I erase this? Yeah. If f is continuous, f from M to R is continuous, then let epsilon be bigger than 0 be the resolution of observer. Be the resolution of observer. So then what happens? So the way I think of continuous maps, one way I think about it, which I'm going to try to also explain for uniform continuity, is that the way I can picture M is if I select a point x here, and we know that this function is continuous at this point x, I can create this water gun that shoots all those points in this interval, shoots them onto the y-axis. So all those points are fed into the gun. And then you see a splash somewhere on the wall, which is here is f of x, and here is your splash. Okay. Now, this splash will look like one point. If I, so to speak, if I feed very tiny interval into this function, then the splash, the stain, will be condensed to one point. And eventually, for resolution epsilon, it will, that's for the observer, right? It looks like one point. Only one point f of x. Is that clear? What I mean by resolution is this. They say if this to you look like 2 points. Now I move them closer, still looks like 2 points. I move it closer, At some point, you stop being able to distinguish if it's 2 points or 1 point. So everything in here is the blind spot for the observer whose resolution is epsilon. So when you are looking at a continuous map, you can think of the observer just judging if this whole open set is 1 point, it's mapped into 1 point, or if it's not mapped into 1 point. Make sense? So the observer, just you are the observer. Each particular one of you has your epsilon, depending on your eyesight. If you are wearing glasses, your eyesight is worse, probably, right? Then you're worse to judge. The smaller the epsilon, the better is your resolution, the better you're an expert in distinguishing whether this is 1 point or not. Correct?
Smaller than my epsilon.
Smaller than your epsilon. Wonderful, right? So for you, it looks like 1 point. That means that you think it's just f of x, okay? So this is what you do with continuous functions. Just for the observer of radius epsilon, everything that is away from a point at the distance of epsilon will be judged as if the heat is exactly, as if everything here is mapped to this 1 point f of x. Okay? So this is where you can then say that m here is so that implies that m can be written as the union of f inverse of balls of radius epsilon, in this case in R, centered at points y, where y belongs to R. You see, I can always write this function as a union. So what does it mean? It means just the union of all things that will be judged by the observer as if it hits to the different points y. Okay? So the ball of radius epsilon around y, the inverse image of it, is all those things that this function, that this water gun will splash somewhere onto the wall, and the observer whose resolution is epsilon thinks it's just the point y. Make sense? If it's the empty set, that's fine, right? That means nothing hits this function. Okay? Now this thing, this is an open cover. It's an open cover of M. Now, this open cover is uncountable. Do you see? Because for every y in R, you have potentially different preimages. So it's an uncountable set, which to observer of radius, basically to the observer whose resolution is epsilon, those are all the possible heat points of this function, right? But if I can reduce it to a finite subcover, it looks pretty much like this case. If I can reduce it to a finite subcover, it looks as if it's just a few points. If this cover can be reduced to a finite subcover, let's say the finite subcover will be f inverse ball of radius epsilon y1 all the way to f inverse ball of radius epsilon yn. Then this function looks like what? Then the observer of resolution epsilon thinks that f of m, the image of m, is what? Here is the point if you understand it or not. So the observer of resolution resolution epsilon thinks that the image of this function m is what?
Those endpoints.
Those points, precisely. You all see that, right? It's a very easy idea, but it's very hard to put in words. So I'm not quite sure if I explained it adequately. Do you follow? Right? So what is this? This is the set of points that the observer thinks are y1. Right? Because the observer cannot tell if those points are mapped within epsilon to y1. So the observer thinks that it's just y1. So this is just y1 all the way to yn. So therefore there is a max and min. You see, it looks like a finite set under the image of every continuous function. That's really why this is important to have arbitrary open covers, because this does not, you don't know what the shape of this, right? It could be very complicated. I just showed you what happens if you feed a ball of radius delta. But the pre-image of this interval, there might be many other places that are splashed into the same region, right? So, I mean, maybe I should draw a picture of that. So if you look at a function like this, okay. So then let's say we look at this point y, and we see what's the preimage of radius. So of radius epsilon. The preimage of that will be, let's make it actually, it has more stuff to it. So the preimage of that is this region, and also that region. So in general, the cover will be, and this is only a one-dimensional drawing, right? So in general, the open cover will look like some sort of weird combination of shapes. Okay. So the conclusion is, in particular, that you can see from this definition, it appears that every continuous function f from M into R has both max and min. Okay, that's really the point of this open cover business, as I understand it. So first, the dilemma is to relate the definitions of compactness. So first is that in a metric space, M, the following are equivalent. So A, if G is any collection if G is any collection of open sets such that M is contained in the union of the sets G such that G is an element of this collection. Then there are finitely many subsets. Then there are finitely many sets G1 through Gn such that M is contained in the union from k equal 1 to n of Gk. So that's the open cover characterization. Yep.
I just don't know if this G is the element of.
So what is, very simply, what is this big G? Give me, like, without mathematics, just what is this? Yeah, but you're talking like mathematicians. Like you go on the street, you explain what is this G, what is that?
Big letter.
Yes, it's a big letter. That's a good explanation. I like it. Well, again, I'm forcing my. I'm sorry. I'm forcing my analogy. That's not fair. But I like it. Right? It's what is it? I can show you. I have those things in my G. Is just like my coat. I have a bunch of napkins there. Right? So this is just a collection of tissues, paper tissues that you use to cover your stain. Okay? That's what this G. So what it means is that we have a bunch of napkins that cover the stain. Yes? No?
I don't know what.
That's the big G.
That's the big G, and this is the little G.
Okay.
Okay. Sorry. More than I needed. Okay. So it's clear, right? So this is the open cover. If you have something that, if you have a box of tissues that can cover the set M, then A is saying that for any such box of tissues, you only need to use finitely many. You don't need to use a lot. Make sense? And part B is something that you don't see much, but really you need this only for the proof of, I mean, well, so that you can relate the definition of compactness as complete and totally bounded to the open cover business. So if F is a collection of closed sets such that any finite subcollection one second. Such that any finite subcollection closed set such that any finite subcollection its intersection is not empty for any then the intersection of all of them is going to be non-empty. Okay. So before I prove it, any idea why open sets are labeled by the letter G very commonly and closed sets are labeled by the letter F very commonly? Yes, but it has to do with language. So, do you know how you say closed in French? No?
Fermé.
Fermé. Very good. Fermé. So those little those F's are closed sets. It's fermé. And how do you say open sets in German? Not quite open actually, but you know, right? Geöffnet eigentlich nicht. That would be a good idea, but they call it Gebiet. For some reason, right? But geöffnet, that's open sets, right? So so actually, Gebiet is usually just a region. It's more than open, usually open and connected. But as far as I know, G stems from that. Okay, it's the German word, and we're going to go into category. We're going to go into talking about Borel sets, right? And then you will see countable union of closed sets and countable intersection of open sets. And countable intersection of open sets will be labeled by the letter delta for Durchschnitt, for intersection, and sigma for sum. I guess that would be unions. Okay, so it comes from both French and German. I like that. Right? Okay, so let's prove this. Actually, proof is very easy. So let's just quickly sketch it. What's the proof? So we want to show that they are equivalent, okay? So we have that A implies B. How we know that? Well, suppose we have this this finite intersection property. So that's B, right? So then, if by contradiction, if the intersection of the sets F such that is empty, that implies, so if we find that the intersection of those sets is empty, that implies that the complement, which is the union of F complement, where F is, what does it imply? It implies that this contains the set M, correct? Where now this is an open cover. So this is now an open cover. So then we can take a finite subcover. By part A, we can take a finite subcover. So that implies that by A, that F1 complement union Fn complement contains M, which then implies that F1 intersection F2 intersection Fn is the empty set. Okay, so that shows you that A implies B, and the proof that B implies A is exactly the same. You can just go the other way around, okay? Okay. Just go begin from there, and you get to part A. All right, so then the theorem is, of course, that M is compact, that is complete and totally bounded. If and only if M satisfies A or B, hence both conditions of lemma. All right. Proof. All right, so first let's assume that condition A is satisfied. So of course we then have B. So what we need to show is that the space M is both complete and totally bounded. So how do we do that? How do we know that M is totally bounded? That's pretty easy. M is totally bounded. Why?
Because the open cover that you pick is just...
Yes, exactly, right? So open cover of size epsilon by balls of size epsilon of radius epsilon is just a particular open cover. Hence, it has a finite subcover, and that means that M can be covered by finitely many. Balls V1 of V of sub epsilon of x1, V of epsilon xn. Okay, so it's totally bounded. Done. Now, how do we prove completeness? Yeah, we need B precisely, right? That's really why we needed B. M is complete. Well, if you pick a sequence, pick Cauchy sequence. Xn. Then let A sub n be the set xk such that k is bigger than or equal to n, and we'll take the closure of that set. Okay, so what is an? Is just the truncated Cauchy sequence. You just delete elements 1 all the way to k minus 1, all the way to n minus 1, and that would be A sub n. Then what do we have? We have that A n are closed sets that have the finite intersection property. With finite intersection property. Which implies by B, which is equivalent to A, right? It implies by B that that the intersection of k equal 1 to infinity of an is not empty, which implies that the sequence converges. Okay? Do you follow?
Is there anything do we need to show that the intersection contains exactly one point?
Well, no need actually, because the intersection has to contain exactly one point. In this case, well, we know the sequence is Cauchy. That's why we know that it contains exactly one point. If you are deleting elements, the diameter of the set AN diminishes to 0.
But we don't know necessarily what the closure is.
No, that's actually possibly an exercise I will assign to your exam, right? Is that to show that the closure is not for the closure of a Cauchy sequence? What could it possibly be?
I know we know.
When you know it, right? No, but it's fairly easy to show. Why? Because when you take the closure of a Cauchy sequence, what do you have? You have an element is contained there if it's a limit of a subsequence, correct? If it's a closure, that means that elements of this subsequence are arbitrarily closed. Either the sequence is eventually constant, right? Or which in this case we don't need to add anything to the closure; is just the same as the set. Or some elements of the Cauchy sequence are arbitrarily closed. Therefore, there is a convergent subsequence. If there is a convergent subsequence, the full Cauchy sequence must go there. So it's actually pretty clear, right? It's clear, I hope. I'm not saying think about it, right? It should be clear. Is it clear? All right. So the other part of the proof is a little bit more complicated. So now what we're going to do, we're going to now assume that that our set is compact. Assume M is compact. So by that I mean complete and totally bounded. So we're going to go by contradiction. If there is an open cover G that has no finite subcover of, or let's say of M, of course open cover of M, that has no finite subcover, we will derive a contradiction. So we have that M is totally bounded. Which implies that M can be written as the union of k equal 1 to n of A sub k, where, and that's very important, let's see if you see this point, where each AK is closed and diameter of each AK is less than 1 or equal to 1. Okay? Why can we do that? So remember the characterization of totally bounded sets. One of them is that the definition that you can cover it by open balls of radius epsilon. The other, which is more intuitive, something is totally bounded if you can rip it apart into subsets, each of which is of diameter less than epsilon for any epsilon. And such that the pieces that you ripped it into, there are only finitely many such pieces. Does it make sense? So instead of cutting it by open balls, you can actually use the open balls to do this cutting into pieces. You can just take the set, tear it apart, and each piece is very small, and you only have finitely many pieces. If something is not totally bounded, you can tear it apart to tiny pieces, but you'll have infinitely many of them. That's the only way. Okay, that seems very unintuitive. I mean, you cannot even imagine such things because you're in Rn. Usually, when you tear things apart here, you see that's pretty obvious that you only have finitely many pieces. Okay. So why can I ensure that this set is closed? That's the question.
You just take the closure of all the open sets.
Exactly. Take the closure of those open sets and you have it. Very good. So it's. I hope you see that it's obvious. I can rip the M apart into the closures of those sets. That's good. You can just rip it apart and take the closures of each AK, and the diameter is not going to grow. So you see, another way of doing that is just because if you say use the open balls to do that, maybe some pieces of the closure that you don't know where they go. So if you're very precise about it, what you can do is, that's an exercise maybe for the exam, show that if you take closure of a set, the diameter does not grow. Diameter remains exactly the same. So what you can do is just rip it apart into into finitely many subsets, and then take the closure of each subset, the diameter will not grow. By the way, they don't have to be disjoint. So what I said is you need to worry about it either. All right. So then without loss of generality, A sub 1 is totally bounded, and it has to be, so without loss of generality, A1 cannot be covered by finitely many subsets in G.
Is this kind of using the pigeonhole principle?
Yes, well, somewhat, right? Well, it's simpler. If each of them can be covered by finitely many subsets of G, then M is covered by a finite subcover, right? So I think it is, right? The pigeonhole principle, right? Or something very similar to it. Yes. A1 cannot be covered by pigeonhole is a little more precise, where you have basically more than one. Yeah, but yeah. A1 cannot be covered by finitely many elements in G, which implies that A1 is infinite, and of course also totally bounded. And totally bounded. Because A1 is a subset of M, and a subset of a totally bounded set is totally bounded. Okay? And infinite, because if it's finite, clearly it can be covered by, just take each element and take an open set that contains that element. It's an open cover. It has to contain everything. So, okay, so then what do we do? Then we take A1. So tear A1 into break A1 into finitely many closed subsets. So A1 is going to be equal to the union. So N1, so K equal to 1 to N1 of A1K, where A1K has diameter, or maybe I'll write it like that, where diameter is less than or equal to 1/2 for all k. Regardless of generality, let's call it A11, which I'll relabel as A2. I'll call it A2 now, cannot be covered by finitely many elements of G. So, because if it could, if all of them could, again, that means that A1 is covered by finitely many elements of G, and that means that M is covered by finitely many elements of G. So what we have is that the implication is that we now have that A1 contains A2, contains AN onwards, where AN is closed, diameter of AN is less than or equal to 1 over n, and AN cannot be covered by finitely many elements in G.
Can you repeat again why that's true? Why A2 and in general AN can't be covered by finite?
Yes, that's a difficult point. So what you have is we are assuming that M cannot be covered by finitely many elements of G. Now we also assume that M is totally bounded for now, right? I didn't use completeness yet. I assume that M is totally bounded. So first part is that I can tear M into pieces of radius of diameter at most epsilon, each piece. And each piece is closed with Pokelot, right? So because there are finitely many pieces, there must be one of those pieces is also not covered by G. Because if you see what you do is, if each piece needs only finitely many elements from this napkin box, that means that all of M will be covered by finitely many. Just use finitely many for A1, finitely many napkins for A2, A3, etc. So that would imply that M is covered by finitely many elements of G. We assume that's not the case. So that means that one of them is not covered by finitely many elements. And then we now take this as our new set. We're going to tear it apart into smaller pieces, each of them of radius 1/2. Then one of those pieces cannot be covered by finitely many elements of G. Do you see that? Because if, again, we have A1 is not covered by finitely many pieces, or finitely many napkins in G. So if I rip it apart, one of the small pieces of A1 is not covered. So you see what I do? I just basically continue tearing and decreasing the size of the sets in this way. And each of them is not covered by finitely many elements of G. Because if it happens that at some point we stop, then that would imply that M is covered by finitely many pieces. Yep. So what does this remind you of? So we have now a decreasing sequence. And the decreasing sequence is that of closed sets, right? So the intersection is non-empty because we now use completeness. Since M is complete, the intersection of n equal 1 to infinity of A sub n is not empty. Now remember, it's very important that the sequence we are now using, that's by the nested set theorem. That's basically completeness is equivalent to the nested set theorem. In fact, the intersection contains exactly one element. Okay? Do you see why?
Diameter is shrinking.
Diameter is shrinking. If diameter were not shrinking, you see, if diameter were not shrinking, you could have had a shift. So it's not necessarily true that the intersection is non-empty just because you have a decreasing sequence. That's only true if the diameter is shrinking to 0. Yeah. So what do we have? So let G sub x be an element of this cover G that contains x. Then for large enough n, A sub n will be a subset of Gx, which is a contradiction. Why is it a contradiction? Must be honestly torture to listen to this part, and that's how I feel. Do you see why it's a contradiction? So first of all, do you see that, okay, so we have this intersection of closed sets. Of closed sets whose diameter is vanishing to 0.
Does that give you a finite subcover?
That gives you actually not only a finite, it gives you a subcover of exactly one element. I mean, for M, of course, but you see, each AN, by our construction, each AN cannot be covered by finitely many elements of the cover G. But we know now know by completeness that the intersection of those closed sets, nested interval theorem, right? The closed sets, they will all intersect to one point, exactly one point. Now, that one point has to be covered by some element in this collection G, because M is covered by this collection. So that implies what? That you see, so each AN, I skipped that step. Each AN contains the point x, obviously, because x is the intersection. So that will force AN to be an element for a big enough n. That will force all AN to be subsets of this GX, and that's the contradiction, because that implies that eventually AN are covered by exactly one element, but they are supposed to not be covered by finitely many elements. Okay, let me just give you a quick comprehension check to see if you remember the nested set theorem. So the comprehension check, suppose that, so true or false, if A1 contains A2 is a sequence of closed sets, in a complete metric space, then the intersection is not empty. True or false? Think about it.
think it's false.
I think it's true.
Wait, no. It is allowed to be empty. The intersection is allowed to be empty. That's what I want to say.
So that means that it's false, right? According.
Yeah.
Yes. Okay.
But
Okay.
since it's a complete space, the sets are also.
Of course, example, right? I'm requiring that the set is, so we have completeness, and I notice I require that they are nested. So each of them is inside of another, and so that's not trivial. Each of them is non-empty. So that A, K is not empty. Otherwise, it's boring, right? Right, of course, right? So A, K are not empty. If one of them is empty, sure, right? This can happen. And the intersection will be empty, but all of them are non-empty.
Take natural numbers with a discrete metric, and then just take 1 to infinity, and then 2 to infinity, and 3 to infinity.
Wonderful,
infinity.
right? But you don't even need to go to discrete metrics. That's an excellent example. But you don't need to go to discrete metrics. You can do that with R, right? This is the same thing that you just said with R. So the answer is that this is false. And the reason it's false is because I didn't say the diameter goes to 0. So let me pretty much your example, but just with R. So, for example, take a n to be the set from n to infinity. Okay? So you don't need discrete. You can just take this, right? Then A1 contains A2 contains A3 and so on, but the intersection where n1 to infinity of A sub n is empty. You see that? Because so to speak, you see, infinity is that missing point. If it were, by the way, but now if it's what you like calling one-point compactification, right? That makes infinity. Well, you know, when you have this. Should I even mention that? But when you take the real number line and you take the reflection of the real number line onto the sphere, not onto, but you take it, you reflect it in the sphere, then minus infinity and plus infinity, they go to the north pole of the sphere, and then the answer is this intersection is the point infinity. Actually, this is not a closed set.
Exactly.
Right, but you see, so the crucial step in our proof was that those sets were closed and their diameter was vanishing to 0. You see that in this example, the diameter is not vanishing to 0. Okay? Make sense? Don't be so sad, right? I know it's a little technical here. Maybe quite a lot of technical, right? But all right, so begin the next topic. What do you say? Yes.
What's the next topic?
All right. May I erase the board? All right, the next topic, well, at least a little bit easier, I think. Well, for a moment. Uniform continuity. All right, so a function f from m to n is continuous if for any x belonging to m and epsilon bigger than 0, there is a function delta of x and of epsilon such that f applied to the ball of radius delta of x epsilon centered at x will be contained in a ball of radius epsilon around f of x. That's the definition of continuity. Right? Ponder about it for a few moments and I'll be back.
Oops, excuse me.
What was that? You okay? So you're okay, guys? Everything's fine? So what does this definition mean? Well, let's suppose that we have this picture here. So this is your n, and this is your space M. So definition of continuity is just, again, very simply is that if you keep your open ball focused at some point x, then its image is going to be very, very small. If you're going to reduce this size of this open ball, if you're going to push the walls closer to x, you're going to push the walls on n closer to f of x. Okay, so that means that the spray of this water gun is going to be more and more focused at the point f of x. Okay, that's just the definition of continuity. Now, a definition of uniform continuity is one where you are now going to allow this interval to slide. So you're now going to take this water gun and you can make it slide from left to right as far as you want. And you can select an open interval that you're going to keep fixed to be some delta. And no matter where you slide, the spray is not going to be very large. So in this picture here, this function is continuous, but not uniformly continuous. Do you see why? So a function is uniformly continuous. Write it here. M is uniformly continuous if delta of x epsilon is actually just a function of only epsilon. Okay? And what this means is that you see that here, if I select a different x, if I slide this interval into another place, I keep it exactly the same size, but I slide it to a different place. So now this is y. You can see that it's going to grow. No matter how small I select the initial delta, as I push it farther out, this is going to grow. This orange interval is going to grow if I move it in this direction. So that means that delta will always, in order to keep it really small, to keep it focused at the center of this interval, or basically focused at f of y, not necessarily the center of the interval, I will need to be sure that the interval also diminishes in size. Correct? All right. I guess we'll call it a day, right? Since the time is up, and we'll continue. We'll just discuss that next class on Wednesday, I hope.